In this tutorial, we are going to learn how to estimate a logistic regression model. And specifically, we'll learn how to do so in R and learn how to estimate a simple logistic regression model, which means that we have one predictor variable and one dichotomous outcome variable, or a multiple logistic regression model, which means that we have two or more predictor variables and a single dichotomous outcome variable. So to get started, go to File, New File, R Script, open up our R Script editor here, which will become our R script file when we save it. And let's make a note here that this is logistic regression that we're doing in this tutorial. So as an initial step, let's make sure that we set our working directory, and this is the folder in which the data that we're going to be accessing for this tutorial resides. And so I'm going to use the setWD function from base R. The name of my working directory folder is my HDrive R workshop folder here. And I'm going to use that as a sole parenthetical argument here in the quotation marks, and then click Run there on that line. Alternatively, you could go to Session, Set Working Directory, and Choose Directory to do the same thing through dropdowns. The next thing I'm going to do is read in the data. And I recommend using the reader package because specifically it has a read_CSV function that's quite useful, fast, and tends to read in the data more accurately. And so if you haven't ever used it before, make sure that you do the install.packages function with the reader package, all lowercase, R-E-A-D-R, in quotation marks. I've recently installed it, so I don't need to do that again. You might need to install this if this is the first time you're doing it, or if you need to update it, in which case you would run that line there. At the very least, you need to use the library function with the reader package with name as a sole parenthetical argument here, and definitely run this line here so you can access the package and the function that we wish to use from it, which is the read_CSV function. Let's call this data frame object that we're about to read in, let's call it TD lowercase, and use the left-handed arrow operator to assign the data frame to this object. And so again, we're going to use that read.csv function from the reader package, and the name of the data file that contains the data we're going to work with today that is residing in our working directory folder that we just specified is turnover.csv, and that's turnover with a capital T. So go ahead and click Run there, and you'll see that the data successfully read in. And note that we have our data are going to be numeric here, and except for the ID variable, which is character. So go ahead and click on the data frame object name in your global environment, which is TD. So here we have the ID variable here. This is a unique identifier. This will actually come in handy when it comes to outlier removal as part of this demonstration today. And then notice that we have the outcome variable here, which is turnover, where 1 indicates that someone quit. 0 means that they're still currently in the company, at least at the time at which these data were collected. So this is a dichotomous or binary outcome variable, which means it's appropriate for a simple or multiple logistic regression model. And then let's assume that we have these data, which are from, let's say, an employee survey, an annual employee survey. We have JS for job satisfaction, OC for organizational commitment, TI for turnover intentions, and NAF for negative affectivity. And so let's assume that these each range from 1 to 5 here, okay? And so these are their overall scale score variables here. So we will start off by, in this tutorial, looking at, does JS, job satisfaction, predict turnover behavior here? Okay, so let's talk quickly about the statistical assumptions that need to be met in order to run and interpret a simple and multiple logistic regression model. Okay, so the first one is that we want to make sure that the cases are randomly sampled from the underlying population so that the cases are independent of each other, relatively speaking. If you assume that if you imagine there's any nesting in your data or anything like that, like there's clear patterns where people are nested in teams and things like that, and you think that might have, that might explain some of the variation perhaps, that would be a different case. And in that case, you'd want to use a multi-level logistic regression model. Okay. In this case, we're going to assume that these cases were randomly sampled. Each person that's in the sample, let's assume that they had about an equal probability of being included, or rather a known probability of being included. Okay, the next one is that the data are free of bivariate or multivariate outliers. Okay, and we'll learn how to test that using Cook's distance as a diagnostic tool here in this tutorial. This will be very similar to the multiple linear regression and simple linear regression tutorials in that regard. Now, the third statistical assumption is the outcome variable is dichotomous, which is another way for saying binary. So there need to be only two levels to the outcome variable. Here we have 1 and 0. 1 is quit, 0 is stayed. Okay, the fourth assumption is going to be that the association between the continuous predictor or any continuous predictor variable and the Logit transformation of the outcome variable is linear. And I'll show you how we can test that using the Tidwell test here later in the tutorial. We get into actually testing these statistical assumptions. And then finally, in the case of multiple logistic regression, meaning we have two or more predictor variables in the model, then we need to make sure that the model is free of collinearity, which is sometimes called multi-collinearity. So we'll get to that one later on. So let's start with a simple logistic regression model. Okay, so we are going to be using the lessR package and specifically the Logit function from that lessR package. So if you've never used the lessR package before, make sure you go to install.packages and then in quotation marks, type in lessR with a capital R and run that. I've recently installed this package here. And I do recommend that you update this package fairly regularly because David Gerbing, who develops it, does do regular augmentations to it and adds additional features. So at the very least, though, you need to use that library function with lessR as your sole parenthetical argument to access that package and the functions that reside within it. So go ahead and run that line there. So here we've accessed the lessR package. You can ignore the masking here. We're not going to be using any of these two functions, either of these two functions that come from the psych package. Okay, so as I mentioned, we're going to be using the Logit function, and that's Logit with a capital L. Now, another name for logistic regression is a Logit model, and that's where this comes from. Okay, we're going to specify this just like we did with simple and multiple linear regression models, in that we specify our model as the first argument. And so first we're going to specify the outcome variable, which if you recall is turnover. This is our dichotomous outcome variable, so turnover with a capital T. Our predictor variable is going to be JS, which is capitalized, so capital J, capital S. And then the second argument is going to be data equals and the name of the data frame from which both of these two variables come from, which remember we read in the data and assigned it to an object called TD. All right, so I'm going to open this up just to make sure there's enough space for this plot to run properly. And I'm going to click run to run this function here. And so this is your output here that shows the relationship between job satisfaction and turnover here. You can't really see it here on mine. Let's see if I zoom. Yeah, you get a little bit of it. But what you would see is a sigmoidal curve in some cases where this is how to best fit these Logit models here. And this is why this is not technically a straight line. If you want to learn more about this, check out the video lecture on logistic regression, as well as the written version of this tutorial to learn more about the underpinnings of and some of the underlying mathematics in terms of how these logistic regression models or these Logit models are fit. Okay, so let's focus in on the output here. So like most lessR functions, we get quite a bit of good output here, and some of it pertains to our statistical assumption test. So before we get down to the statistical assumption test, I just want to point out a few things that are useful here. This will confirm for you what your data frame object is, your response variable, which is another name for your outcome variable, is turnover. Your predictor variable in this case is JS, which is for job satisfaction. And then we get some useful information about, okay, how many cases or rows are in our data frame, and here we see 99, but how many were actually retained for the analysis? 98. So what this analysis does by default, it drops does list-wise deletion for anybody that has missing data on one of these two variables here, either your response, your outcome variable, or your predictor variable. So the next thing that we're going to do is let's talk about these statistical assumptions here. So the first thing that we want to assess is are these randomly sampled? Well, we're not going to find that out from our output here. This is something that, let's just assume that these variables or these cases, these people were randomly sampled from the general population. So let's assume that we've met that one. Okay, so I'm going to say met this one. The next one that we want to assess is the outcome dichotomous, meaning are there only two levels to the outcome? And that has been met. We already established that. It's 1 and 0. 1 equals quit, 0 equals stayed. Now, what about the data being free of bivariate or multivariate outliers? In this case, it's bivariate because we just have two variables in our model, free of bivariate outliers. Okay. And so how do we determine if this is met? Well, let's take a look at our output here. And so let's scroll down. And this will be just like simple and multiple linear regression output from the lessR regression or the reg brief functions, in that we can look at the analysis of the residuals and influence table here, and we get some information about the data, the fitted values, residual values, the studentized residuals, as well as Cook's distance. We're just going to focus on Cook's distance here, but I want to explain some other aspects of this table. And so here you can see these are actually selected based on Cook's distance here, but I'll show you. These are the unique row numbers for the people in the data frame, okay? So if you go here, TD, the row numbers are in this shaded column here to the left. So 69, that person is EMP 873, okay? So that's how you interpret that. And so for that person, they had a score, observed score of 6 on JS, job satisfaction, and they had a score of 1 on turnover, which means that they did quit. And then here's the predicted value here, or in other words, the fitted value. It's 0.31. Okay, so this is a probability here, a proportion. And so what will happen later on when I'll show you a special table, a classification table, what is going to happen behind the scenes is that anybody that has less than 0.5 in this value, they'll be predicted to have stayed. And anybody such as this person that is greater than 0.5, equal to or greater than 0.5, will predict that they have quit. Okay. And so you can kind of come through here and see, well, actually these first two seem like they're a little bit off here. And so this is maybe why they are, might be deemed outliers here, or part of the reason. Okay. So and then the residual here is just, in this case, what is their observed value? 1, they quit. Minus their fitted, you get their residual, okay? So this is how much error you have in prediction, in other words, or error in the fit. Okay, so the next thing that we want to focus on is this column that has the Cook's distance or Cook's D values here. Now there's different rules of thumb that you might use to determine what is a meaningful Cook's distance, but typically you want to pick out the ones that seem to be especially high. This is a very coarse rule of thumb, but generally if you start getting above 0.4, I would start being a little bit concerned. And definitely if you see some that seem to be outliers, and in terms of being much higher than some other groupings of them, these are good candidates for being potentially influential cases and maybe ones that you consider dropping. But don't drop people lightly. This is something that you really want to have a conversation about this. Look back at them. Make sure that their data were entered properly, that sort of thing, that they're actually part of the population of interest. And I'd say as a last resort, consider dropping them. But make sure you have a good case for doing it, and knowing the Cook's distance value can be the start of that case that you build. Okay, so looking at this, well, we kind of see these two people, which are the people associated with 69 and 7 row numbers. They have the Cook's distance values here of 0.084 and 0.062 that seem to stand apart somewhat from the rest of them, okay? So for the sake of this, let's imagine that these two people, that might be potentially bivariate outliers, okay? And we're really just going to do this for demonstration purposes. If this were me, I probably would leave these people in, okay? But let's just make a note here. Row numbers 69 and 7. So that's where I'm getting these two values here. And so we need to actually grab what is their actual unique identifier value. And the way we do that is visually examine the data here. So we see 69 is imp 873. Let's put this in parentheses here so we can draw on it later. And then 7, row number 7, which unique identifier does that belong to? EMP 607, okay? All right, paste that there. So we'll come back to that for later, but we could assume that this has been met. But for the sake of demonstration, we'll come back and pretend like it hasn't been, and we're going to remove those cases later on. Okay, so we don't have to worry about collinearity because this is just, we have a single predictor variable, but we will worry about that when we get to the multiple logistic regression model. So the next thing that we do need to worry about is that the association between the predictor, I should say continuous predictor, and logit transformation of the outcome, because that's what we're talking about here with the logistic regression model, is linear. Okay, so how do we determine whether that's been met? Well, we're not going to find this in our output here, but what we will do is that we can run a test that's called the box Tidwell test. This is one way that you can go about doing this. And so the box Tidwell test, we're actually going to create a log transformation of the JS variable, which is our predictor. And so what I'm going to do is copy our logistic regression model here, click paste, and I'm going to add, using the plus sign, the JS variable again, and type colon, and then log, which is the function to do the natural log or the a logarithmic transformation of a variable, and then type the name of the variable again within the parentheses. And what this will do is if we find that the interaction between the variable and the log of that same variable, if that term is statistically significant, that might be evidence that there is a nonlinear association between this continuous predictor variable JS and the logit transformation of turnover here, okay? So let's go ahead and actually what I'm going to do here is use the, well, let's just do the add initial argument here that is just brief equals true, so that we'll get less output here, okay? So let's go ahead and click run. All right, so let's take a look here. We're really only coming for one thing, and that is we are looking at this line right here in our model coefficients table, and really what we're peeking over at is the p-value. So this is the interaction term between the JS variable and the logarithmic transformation of that JS interval, and we see that it is equal to, or is greater than or equal to 0.05. So this would mean that this is not a statistically significant interaction term here, and so therefore we don't have evidence really in this case that there is a nonlinear association. Now, if you did find a nonlinear association, that is a whole other thing that is beyond the scope of this tutorial. You can check out another tutorial that's called Polynomial Regression in R that gives a little bit more information on how you can assess associations that are nonlinear and maybe specifically have a quadratic relationship, or a quadratic function is the functional form, or a cubic function is the functional form, or quadratic would mean that you have a single bend or in your nonlinear association. Cubic would mean you have two bends. And this is beyond the scope, again, of this tutorial, but check out that polynomial regression function in our tutorial in R if you do come across this issue in some of the data that you have in real life. Now, another thing that will happen if you, let's say this JS variable, we can see here that it does not have any 0 values or negative values. And actually, I misspoke before. This is actually, these variables range from 1 to 6 instead of 1 to 5, now that I look at this. And so anyway, that's inconsequential for this. But if you had seen a value of 0 or negative, that's going to be a problem if you're taking a logarithmic transformation of the variable. And specifically why that's the case is that the log of 0 or a negative value is mathematically undefined. Okay, so you will get an error message if you do that, guaranteed. So if you do come across a situation in which you find that this variable that you're working with has a value of 0, maybe you've group mean centered it or something like that, or it just naturally has values of 0 or negative, then you will need to do some type of transformation. And specifically, you'll need to transform it so that the values, you don't have any negative values or values that are equal to 0. For way more information on this, check out the written version of this tutorial in which I go into greater depth on how you might do that. But one of the best ways to transform, or one of the most typical ways, I should say, to transform it, if you run into that issue, is to convert this variable just for this box Tidwell test, convert this JS variable such that the lowest value becomes 1. Okay, and there's different ways you can go about doing that. The written tutorial shows you some of those, or one of those specifically. Okay, so let's say that we have met the assumption that the continuous predictor variable, the logit transformation of the outcome variable, that's a linear association. Okay, so what I'm going to do next is I am going to, just for the sake of this, I'm just going to remove that information and just get us back. This is the original function that we had in the original arguments, and just rerun it so we can refresh this down here. Okay, so now we're ready to actually interpret the results because we've met the statistical assumptions, or feel reasonably confident that we have. Okay, so what we're going to do next is we go down to the basic analysis section. We look at the model coefficients table here, and we're generally not that interested in the intercept unless we want to use this regression model to predict future cases, which could be something we want to do, but usually the p-value associated with the intercept is not super informative to us. But what we do want to do almost certainly is look at this line here, which is our predictor variable JS, the regression coefficient associated with it. So this regression estimate of that is negative 0.438 about, this is its standard error, this is its z-value, this is its p-value. Its p-value is less than 0.05, which is the conventional two-tailed cutoff for statistical significance. And so here, because it's less than 0.05, we would conclude that this is a JS does have a statistically significant association here with the logit transformation of the outcome variable. So as I just said, though, this is the logit transformation of the outcome variable, which means that this is not going to be by itself in its raw form, this estimate here, that meaningful to interpret. If you wanted to interpret this, you would say something like, for every 1 unit increase in JS, the logistic function decreases by 0.438 units. Okay, not super informative. But we do know that there's a statistical association and it's negative, meaning that people who have higher job satisfaction, there's some tendency for them to be less likely to quit or turn over. Here's the 95% confidence interval associated with that estimate. What is going to be most useful for us, and what is an actual effect size too, is the odds ratio that's presented down here that's associated with the JS, which is our predictor variable. Now, how do we get here? Well, this odds ratio is simply the exponentiation of this value right here, negative 0.438. If we take Euler's number, so that's EULER's number, and we take that to the negative 0.438 power. So this is the exponent here. We get the odds ratio, and that process is called exponentiation there. Okay, and so if we want to exponentiate this variable or this regression coefficient, we get this value here. Okay, so an odds ratio that is less than 1 indicates a negative association. So we see that here. If it was greater than 1, it means there's a positive association. And so how do you interpret an odds ratio when it is less than 1? Well, if your odds ratio is less than 1, one of the best things that you can do is to take 1 minus the odds ratio. So when it's less than 1, take 1 minus the odds ratio. And so 1 minus 0.646, let's say, is going to be 0.354. Okay, so I'll make a note there. So if we take 1 minus 0.646, and this is going to be 0.354. In other words, this is 35.4%. Okay, so what this means is that the odds of quitting are reduced by 35.4% for every 1 unit or 1 point increase in JS, which stands for job satisfaction. Okay, now if you wanted to think about this from the perspective of staying, you could actually calculate the reciprocal, which would just be 1 divided by 0.646, which is our original odds ratio here. Okay? And if you take 1 divided by 0.646, what are you going to get? Well, let's calculate that here in our output. So 1 divided by 0.646 is 1.548, let's say. Okay? And so how do you interpret this? I'm just going to scroll back up here to the output. Well, in this case, so this would be if we wanted to flip the interpretation, so we focus on those people of staying. And so the way we could focus on this is that the odds of staying are increased 1.548 times for every 1 unit increase in JS. So the odds of staying increase 1.548 times for every 1 unit increase in JS or job satisfaction. So this is the same thing, we just look at it differently. Okay, so the focal point for this first one is quitting, and the focal point for the second one is staying. You can talk about it both ways, one of the ways, whichever way you think is going to be most informative for your audience. Okay? All right, so let's now move through further. We've gone through the odds ratios. This is some information about model fit here. You can technically, with a logistic regression model or a Logit model, you can estimate a pseudo R-squared value. Let's ignore that for the purposes of this tutorial because it doesn't come standard in this output here. But what is super helpful when it comes to assessing how well your model fit the data and how predictive your data are at the model level. And before I do that, I should mention the odds ratios. This makes me think that I should mention the effect size standards. So if an odds ratio is less than 1, here are the standards. Okay, so small is going to be 0.8, medium is going to be 0.4, and these are rules of thumb. So use them as you wish. And large is going to be 0.2. And so in our case, we can see our odds ratio is 0.646. So this is kind of a small to medium sized effect there. Okay. Now, if your odds ratio is greater than 1, then I'm just going to copy and paste this so I can replace some of these values. Then a small value is going to be about 1.2. And there's some variation on this in terms of what people's common rules of thumb are. A medium is going to be 2.5, and a large is going to be 4.3. So if we were interpreting the reciprocal of our odds ratio as 1.548, you can see that that falls in between small and medium too, which you would expect. Okay, so as I mentioned, if we're talking about overall model fit, let's look at the classification table. This is the last thing that's going to appear in your Logit output. And so here you see the classification table for turnover. So 1, of course, means quit. 0 means stayed, according to our data. Okay? This is the baseline data here. So in other words, this is how many people in your raw data frame stayed versus quit. So 39 people stayed, 59 people quit, of the people we had available data for. So this is 98 here total. So 39 plus 59 is 98. And then you get the percentage here. Okay? So you can see that over half the people quit. So we had a turnover problem here, and then less than half stayed. What we're most interested in here, though, is the predicted side. And so here you can see we've got a 2x2 table. So the rows here represent the actual observed values of who stayed and quit. And then predicted is the fitted values, or those people who we would predict to stay, which is 0, or 1, quit. And remember way back up here in this table, I showed you these fitted values and said that if it's less than 0.5, we would call that 0. We'd round down to 0 and say that that person is likely to stay. And if it's 0.5 or greater, we'd say, oh, that rounds up to 1. That person is predicted to quit. That's what's happened here in this table. Okay, so they took those probabilities and just dichotomized them. And so everybody had to be either fit into stay or quit. And so here you can see the 2x2 matrix. So for instance, this value of 8, that means that there's 8 people that were predicted to have stayed who actually stayed here, okay, out of our sample. this 10 value means that we predicted these 10 people to stay, but they actually quit. So that's an error right there, okay? This 31, these are the people that we predicted to quit, but they actually stayed in real life. And then 49, these are the people that we predicted to quit, and they actually did quit here. Okay, so in terms of interpreting this, when we're thinking about those people and looking at those people who actually quit here, and I mean, those people who actually stayed in real life and how accurate we were able to classify those people who actually stayed, we only had 20.5% were correct. Now, for those people that actually quit, we were a little bit better here. And we found that we were able to predict that with 83.1% accuracy here. What we often are interested in is this overall estimate of accuracy or correct predictions here. And here we see it's 58.2%, okay? So, you know, you can imagine flipping a coin is about 50-50, right? 50% chance that you'll predict that someone correctly. In this case, where we have a dichotomous or binary outcome. So 58% isn't super exciting. That means we're just about 8% above what we'd expect by chance if we flipped a coin. But hey, it's something. And so this is why we add more predictors to our model to predict this predictive accuracy, or to enhance this predictive accuracy and get closer to 100%. Okay? And so in this case, you could say, hey, there's some effect here. We saw that their job satisfaction of JS significantly predicts turnover, but there's still a lot more variance to explain. There's other ways we can improve our model's fit, okay? And so that's what we're gonna do next. We're gonna do a multiple logistic regression model, okay? And so all this means is that we're doing the same thing as before, except we are now going to add additional predictor variables. So we're going to use that Logit function from lessR, and turnover is still our outcome. JS is going to be one of our predictor variables. TI, which is turnover intention, is going to be another predictor variable, and we're just adding plus symbols between these to add more variables. We're creating an additive model here. And then in AF, so negative affectivity, is our third variable that we're going to use here. So let's do data equals, and note that these come from the TD data frame, all four of these variables. Okay, so let's click run there. And you'll see some output here. These are the scatter plots here in case you want to look at those. They're not going to be super informative at this point just because of, at least on my screen, it's kind of hard to see them with these little panels there. But nonetheless, you might want to look at those. Help assess things like determine whether there might be issues at collinearity and so forth, which is one thing that we'll talk about soon. Okay, so again, we get our basic model information here. And one other thing I wanted to mention before we get to this is just to quickly show you how you would, this is our oops, wrong one. This is our regression model, simple logistic regression model. If you wanted to remove those cases we identified above, remember it was employee 873 and employee 607. Those were the people that we detected as potential outliers. You would just use the rows equal argument here, and then we'll add parentheses, and then we're going to use the not symbol. Okay, so that's the exclamation point here. And we're going to say ID. So this is ID variable here, this unique identifier. So the ID variable is not equal to, and we'll use percentage in. So it is not within the following vector here. And in this vector, we're just going to note those exact employee ID numbers. So imp 873 is what we identified before. That corresponded to row number 69. And then imp 607, that was the other one there. Corresponded to row 7. And all we would do is just click run there. And then now you'll see that our sample size is now down to 96 because we've dropped those people, okay? All right, so that's all you would do if you needed to actually remove outliers within the function itself. There's other ways you could go about doing that. Okay, so I'm gonna clear this console, and we are gonna rerun this script going back to multiple logistic regression model now, specifying that model with JS, TI, and negative affectivity as our predictors of turnover. let's see what we're working with here. And so you'll see that the total sample size for the data frame is 99, but due to missing data, we are down to 95, okay, cases that are actually included in the analysis due to list-wise deletion. As we did before, and I'm going to scroll up here and just grab these statistical assumptions up here. So just grab this text. I am going to, we'll walk through each of these for the model. So let's just remember that, let's assume that these were randomly sampled cases. Okay, so that assumption's been met for that statistical assumption. The dichotomous is still outcome. The outcome is still dichotomous, so that's turnover, which is 1 and 0, so that's a dichotomous. That assumption's been met. Nothing's changed there. I'm going to change this to free of multivariate outliers. Okay, let's delete that. And let's just take a look down in our output here at the Cook's distance from the analysis of residuals and influence table. Okay, so we have some new potential concerning cases here. You'd want to look into these further. The first ones that stand out are row numbers 14, 1, 69, and let's say 47. So there's maybe four cases that might be influential and potential outliers. Again, eliminate them at your own peril and think really carefully about removing outliers and have a good, compelling reason for doing so. And the Cook's distance value can be one starting place for building that case. Okay. So let's just assume for this tutorial that we've met that statistical assumption. The next thing that we're going to do is let's add in free of collinearity. And if you remember, collinearity from a multiple linear regression context simply means that our predictor variables are not strongly correlated with each other. And so we'll focus on tolerance. Tolerance is just the reciprocal valence inflation factor, or VIF. And tolerance, I personally find to be more interpretable. So a tolerance of 1 is a really good thing. It means that there's no collinearity or no strong correlations between the predictor variables themselves. A tolerance of 0 is terrible. It means that there's really strong, if not perfect, correlations between the variables. Generally speaking, if a rule of thumb is if the tolerance is 0.2 or less, so closer to 0, 0.2 or closer to 0, then we're concerned about collinearity. Here, these tolerance values are actually pretty good. They're all pretty close to 1. So let's say that we've met the assumption that we're free of collinearity there. Okay, so the next thing that we're going to do is we're going to do a box Tidwell test again. Okay, and so we're going to grab this multiple logistic regression model here, and we're going to do some more logit transformations, log transformations of, well, so we'll do JS, the name of that variable, colon, log function, and JS again. So this is a logarithmic transformation of JS. Do the same thing for TI. So TI colon log, TI is the argument. In F, so negative affectivity, colon, and then log, same variable there. Okay, so now we have set up the box Tidwell test here. We're looking to see if these interaction terms, this one, or this one, indicate, if they're statistically significant, it could indicate that there is a non-linear association between one of these continuous predictor variables and the logit transformation of the outcome. So let's click run. And really what we're going to focus on here is just go into the model coefficients table here and just do a quick trip down the p-value lane here. And let's see, here are the 3 interactions. So each variable and its interaction with its logarithmic transformation of itself. And we're looking for p-values that are less than 0.05. None of these are less than 0.05. And so therefore we conclude that there is not evidence of nonlinear associations between these continuous predictor variables and the logit transformation of the outcome. Okay, so now we can run back. I'm going to clear out this console here, doing a Control L. I'm going to run back. I'm going to grab and copy our original model here so that we can put it down here. And now we're ready, because we've met that final assumption there, that assumption of linearity, we're ready to actually interpret the model, okay? So this is our model with the 3 predictor variables. Let's jump down to the model coefficients table here. these are our regression coefficients. Let's take a look here. Oh, we've got 2 that are statistically significant. So remember, in a model by itself, JS was statistically significantly associated with the logit transformation of the outcome. But here, when controlling for the other 2 predictors in the models, it is no longer statistically significant, as evidenced by a p-value that is greater than 0.05. We do, however, see that TI for turnover intentions and NF for negative affectivity, both of these are statistically significant, and both of these are positive, meaning that higher levels of TI and higher levels of negative affectivity when controlling for the other predictor variables in the model indicate that a person is more likely to turn over or quit, okay? But remember, these coefficients by themselves, because it represents the association between the predictor variable and the logit transformation, or in other words, the logistic function of the outcome, they're not going to be super interpretable by themselves. But if we exponentiate them and turn them into odds ratios, which is automatically provided down here, then we have something to work with. Okay, and so if we come down here to the odds ratios, remember, we're just going to focus on the 2 that were statistically significant. Okay, so the 2 that were statistically significant were TI and NF for negative affectivity. And here we see that the odds ratio is 2.45 for TI. So what this means is when controlling for the other variables, predictors in the model, that the excuse me. So for every that the odds of quitting increase 2.45 times for every 1 unit increase in TI. Okay, and then with NF, it indicates when statistically controlling for the other predictors in the model, the odds of quitting increase 3.30 times for every 1 unit increase in negative affectivity. Okay, so that's how you can interpret it there. As I did with the simple logistic regression model, you could also take the reciprocal of these 2 if you wanted to interpret them from the perspective of those people who stayed. Okay, so we've got 2 significant predictor variables here. Let's scroll on down. And let's look at the classification table now. So you remember with the original classification that just had job satisfaction in it, JS in it, the overall percentage of correct predicted values was 58% about. And now we see that it's 78.9%. So we've increased our predictive accuracy by adding these 2 other predictor variables to the model. And so again, here's our baseline, which is what you would expect. Number of people who stayed, 37. Number of people who quit, 58, where 0 means stayed, 1 equals quit. And then what we're interested in is the predicted over here. So again, just a quick refresher. This right here would be 23 people were predicted to stay, and they had actually stayed. Here, 52 people were predicted to quit, and they actually quit. And then these people in these 2 quadrants were errors. Okay, well, they're not errors, but we estimated them, we predicted that they would do something that they didn't actually do. So what we can say now is looking at this row right here, specifically the percentage correct over here. For those people who actually stayed in real life, we were able to correctly predict that they stayed using this model 62.2% of the time. Okay. What about those people who actually quit? This is this row. We were able to correctly predict who actually quit using our regression model here, logistic regression model, 89.7% of the time. So that's pretty good. Now the overall percentage of correct predictions is 78.9%, which is getting somewhere. You think about this model being applied again in the future to predict the likelihood that people are going to quit. This can be very, very useful. And so you can take your regression model, your logistic regression model with the intercept values and the regression estimates here, and you can actually estimate for each person their probability of quitting in the future. And so this can be very useful because you can identify potentially those people or people who might be at risk and figure out, well, how do we get these people to stay, assuming we want them to stay in the organization. All right, so this wraps up the tutorial on both simple and multiple logistic regression. Now, logistic regression does get a bit more technical than standard linear regression because we start talking about logit or log transformations of variables, and we start thinking about things like the odds or the probability of something happening, okay? And so this adds some complexity to it, but at the same time, this is a really great type of analysis for classification, as we saw with those classification tables. A lot of times, we like to think of things in the binary, especially things that are consequential in an organization, like staying versus quitting. And so the extent to which we can predict those dichotomous or binary outcomes with some accuracy or classify people to accurately to one or the other level of that outcome variable can be quite useful for us in many situations. Okay, so this wraps up the tutorial on logistic regression in R.